Welcome back. In the last class, we started the discussion on the system security part, and in particular, we looked at the various functions the operating system does, and couple of important functions like the process management and the file system management from the security perspective. Today, we'll continue that discussion. And the outline for today's discussion is I have picked a couple of more topics. One is the memory management, and second one, the password and the user account management within the operating system. So let's get started. First, let's look at the memory management part of the operating system. We said that every time a process is created, we don't want one process to interfere with the other process, the existing process within the system. How does the operating system in fact ensures this is the question. So this is done by defining something called the process granularity. What happens is every time a process is created within the system, a memory location, a portion of the memory is actually allocated to that process. If you look at the diagram, the memory itself within the system can be thought of that this is maybe your main memory, and a process when it starts, it's been allocated some address space. So maybe from starting address 1000 to 2000 is given to the process P1. Similarly, if I have other processes in the system, maybe P2 is allocated from 2000 to 3500. It depends how much memory each process requires. The operating system, in particular, the memory management unit of the operating system allocates the requisite memory to each of the process. That is one. So every time the process P1 makes a request, makes a memory reference, the operating system checks whether the reference the P1 is making itself is falling within the starting and the ending address of the that process. So within the let's say one variable need to be accessed or one something need to be written to the memory, then that time the memory management unit need to check whether this reference is falling within this range 1000 to 2000. So by doing this, it actually prevents from one process to interfering with the other process. This is one aspect of the memory management. And the second thing what it does is, on a global level, it divides the memory into two parts. One is the, we said that the kernel is the most important part of the operating system. So a portion of the memory is given to the kernel, and the second portion is given to the user process. So if I can again view the memory, one portion, so this is kernel address space, and the remaining portion is maybe it is called as the user address space. So when I am saying process P1, P2 here, assuming they are all the user created processes, they are falling here. So this is actually blown, you can think of this as a blown up portion. Every application that is run on the system, assuming that is a user process, user application, so that has to fall under this address space. Meaning, every time again a memory reference is done, first check the memory management unit or the operating system does is whether that is falling within the kernel address space or the user address space. If the process is user process, then it has to first the reference has to fall within address space, and once that check is done, the second level check is whether this is falling within the address space allocated to that particular process. So if these two conditions satisfy, then the process that access is allowed to go through. So this is the two level checking that the operating system, or in particular the memory management unit does. So to protect one process from interfering with the other process. This global division of kernel address space and the user address space is deliberate one. Why this is done? Because the kernel is a privileged component. So all the processes as part of the kernel are going to be running in the kernel address spaces. This reference, the address space, whatever I told you, usually that address space is every time the process created is organized into something called as the segments. Segments meaning the address space of the process itself is divided into several sub sections. So these segments are some referred as .txt section, .data section, .bss, .heap, and the stack segment. These are the commonly found segments within the address space of any process. So this is how it look like. So it contains the different components of the program. So every time a program is compiled and then you get an executable version. So that executable version, when that is about to run on the system, the memory map of that process is actually looking like this, and meaning it has got these many components. So let's say, for the sake of example, I have a C program. So let me call that as, let's say, hello.c. If I use some compiler, let's say GCC, I get an object file, maybe the default object file a.out. This a.out contains the instructions corresponding to hello.c program. Whatever is written as a program logic, that gets translated into the machine level language, which can be run on a particular type of the machine. So the compilation process is targeted to a particular architecture like x86 and so forth. So the text segment, what is shown here, is the one which contains the actual instructions of that program. So I said, when I write a program in high level language, when I compile that, the corresponding object file that get generated has got the machine instructions. So those instructions come and sit in this segment, which is the text segment. And similarly, in the program, it might have some dynamically allocated variables. So for example, malloc, calloc functions in C programming language. So such dynamically allocated variables are taking the dynamically allocated or dynamic variables. So dynamically allocated, any variables are there, those variables come and sit in this heap section. And if there are global variables which are initialized, those are going into the data section. So if there are global variables which are not initialized, uninitialized, those are going into the .bss section. And every time a function call is made, so let's take this example. Again, the C program, I have the main function, and then within that I have function f. The definition of f is made here. And when the control jumps from f to this place, when call is made, the return address, the very next instruction after the f, the address of this, let's say the function call f is made at the location 1000, and maybe 1004 is the next instruction. So this address is the place where the control has to jump back after the execution of the function f. So meaning it has to go back to the address location 1004. So this return address is stored as part of the stack. So this is the return address. And along with this, stack also has got the local variables. So meaning if I declare maybe an int a here, so that variable also come and sit in this stack. So every function, main is also a function. So one return address and one set of local variables are there for the main function. And from main to, if you jump to f, there is from f to f1, if you jump, then another set of return address and the local variables corresponding to f are stored in the stack, and so forth. So likewise, if I have hierarchy of functions from main to f1 to f2, so every time there is a jump, so the return address and the local variables are pushed onto the stack. An interesting thing is, the stack and the heap in most of the cases grow in the opposite direction. So mean this is the pre-space. Why this is pre-space? Because I don't know how many function jumps are there and how many number of the variables are allocated dynamically, whether they grow or shrink, I don't know. So in order to accommodate those dynamically changing situations, there is a pre-space and these two actually grow in the opposite directions. So this is how the memory layout of an executing process look like. So as I said, the dynamically declared variables are going and sitting in the heap section. And if there are global variables, static integer is a kind of the global variable because it retains its value across the function calls. So those are in the .bss section. And if there are global variables which are initialized, those are in the data section. So as I said, the various segments are there within the address space of an executing process. Sometimes these the segments themselves are marked as whether they are readable, writable, and executable. This is another level of the protection that the operating system provides, particularly in the memory management unit. So I'll just give an example. Once I compile this, in this case, the hello.c program, and this a.out is generated, the logic of the program is freeze. So I don't change unless I change the program hello.c and then recompile it. The logic of a.out, whatever is the instructions, those should not change. So as I said, correspondingly, where are the instructions? Instructions are there in the .txt text section. So there is no point when the process is running making this writable because the code is anyway not changing when the process is running. So this it makes sense to mark this as not writable. So write permission is not there in the text section. So if you give write permission, sometimes what happens is inadvertently if something is changed, then the whole process you might end up with unexpected scenarios. So that we don't want. So that is why we can mark this section as the not writable. Similarly, the stack and the heap are actually growing and shrinking dynamically. We don't know how many number of the elements should be inserted into the stack and what kind of the variables are declared, whether they dynamically grow and shrink. So heap and stack section need to be writable. Similarly, appropriately, other sections are also marked as whether they are readable, writable, or executable. So where are the instructions? Instructions are in the .txt section. So it makes sense to mark this as the executable section because the instructions you need to fetch and execute. That is one thing. The second level protection is actually given by the operating system by marking this various sections as readable, writable, and executable. Sometimes what can happen is, although I said the memory allocated to the process, the address space to the process, different processes P1 and P2 in the previous example are organized sequentially. So we require maybe 1000 to 2000 is for the process P1 and 2000 to 3000 is process for process P2. But this is how the individual processes see them as the address spaces, their address spaces. But in reality, what can happen is the memory chunk allocated to both process P1 and P2 may not be contiguous. So in that case, what I'm trying to say is, so I require 1000 to 1000 bytes for the process P1. So in physical memory, so this might be the space, half of this one 500 bytes might be given from the address starting with 5000 to 5002, 5500, and similarly from 5500 to 6000 process P2 might be allocated the memory. This is 500 bytes, and then you might have process P1 from 6000 to 6500, and then again you might have P2 link from 6500 to 1000. So this is 500, this is 500. So 1000 bytes that is required for the process P1 is allocated in two chunks, one here and the second one here, and similarly the 1000 bytes required for process P2 is allocated here and here. So in addition to looking at as a memory management unit, whether the memory reference made by a particular process is actually falling within this address space. When I say the address space, it is actually the logical address space 1000 to 2000. So that need to be mapped into or translated into the physical memory. So whether it is in the portion 1 or in the portion 2 corresponding to process P1, and similarly for process P2 also, whether it is falling in the portion 1 or P2, it need to check. So when the memory is divided into many portions, then the memory management unit also need to keep track of where exactly the segments for different processes are allocated and whether it's actually valid reference. That also it need to check. So that is how the memory management unit of the operating system works in order to provide protection, the required protection. What is that? One process not interfering with the other process. So that's about the memory management unit. With that, let's move on to the second component, which is the second component today's discussion, which is the password and the user account management. As if you can recollect the last class discussion, every user has got some privileges. He is allowed to do some actions on this system. Maybe he can create some files, execute some files, delete some files, something like that. And every time such access request is actually made, whether it is read, write or execute, the operating system need to check whether that user is allowed to do so and so whatever the requested action is. How does the operating system actually verify that who is the user logged in and what all he is allowed to actually do on the system? So in order to do that, the operating system do kind of the user account management. The user accounts are stored on the system, and then when he supplies the credentials, so the credentials are verified, and accordingly who is the user logged in, the operating system knows, and accordingly the access controls are actually maintained. So before we actually look into how exactly the operating system, in particularly the Unix and the Linux operating system manages the user accounts, let's build some concept. So what we can do particularly if I want to manage the user accounts on the system, how can actually we can do that? That question. The simplest thing that we can do is, let's say I have got some X number of the users. Here I have shown three users and then their corresponding passwords. One of the simple thing that I can do on the system is I can store the user names and the passwords in a file. So let's say this is the file, and let's call that file as the password.txt, and it has got two things. One is, what is the first thing? It has got the username, and the second one is the password of the user. So maybe the user 1 is there, and then corresponding to that the password 1 is there. This is the password of the user 1. Similarly, I got the second user and then her password and so forth. So n users are there and n passwords are stored. And what I can do, so every time some user tries to log into the system, he supplies two things. One is the user ID, what is the username, and the corresponding password, what it thinks. So you can go back and check in this file. This is a plain text file, whether this UI is there, any of these usernames in this column or this particular column are matching with that username. If so, if let's say U2 is the one which matches and this PI is checked with this P2, if they match, then we say that, or the system says that the password is matched and the user is authenticated. So this UI is allowed to log in. So now what is the issue with this one? So this entire file, since it is a plain text file, when user UI try to access the system access, so he can also read this entire password.txt file. And let's say there is another user, maybe this user is claiming to be UK, the kth user in PK. So he can also read the corresponding file. Every time user is logged into the system, they can actually navigate and then go and read this file. How do I actually protect this file from one user to other user? So UI knowing UK's password and UK knowing UI's password, I need to protect them. So that is why storing the password in a file and having them maintained like this as a catalog of username and password is not the best idea, because everyone can read this file, and then once, or if you lose this file, then the whole username and the passwords are known to everybody. So that is one danger that of maintaining the passwords in this fashion. Now, if this is not a good way, what is the other way we can think of? The second thing that you can think of is, so let's say I have the same password file, password.txt, and then two things. One is the username and the second one is the password. So as usual, I have got n number of the users and then their corresponding passwords. So I can think of, since I don't want multiple users to read this file and know their passwords, I can probably pass this to an encryption algorithm. That encryption algorithm probably can take some key. Let's call that key as K1, and we transform this entire file into an encrypted version. So maybe I can still have this same names. This is just for understanding, and then the passwords. The username U1 is transferred into something else, maybe XYZ here, and then password P1 is transferred into some non-readable PQR, and U2 is maybe ABC. This is 1, 2, 3, and so forth. So all username and passwords are encrypted with the key K1. Now, if some user wants to log into this such a system, and he supplies as usual the UI and the PI, how do I actually verify that UI is a valid username and PI is the corresponding valid password? So when the user supplies this, I need to do the reverse operation of what I did here. So I take this encrypted file as the input, and the second input is the key K1, and then I do the decryption of this file. So this is an encrypted file, so I do the decryption. I get the decrypted version of the file. So again the usernames and then the passwords are there. Now if I do the decryption with the same key, I should get back all the usernames and the corresponding passwords. So from U1 to UN and P1 to PN, all of them. So then once the file is in this format, I can take these two entities and check whether this is a valid username, if so, and what is the corresponding password of that user. I can check and verify. So at the outset, the decryption happens. The file is actually only in readable format only when certain user is actually logging into the system. This seems to be a workable solution, but the problem is, once the file is actually decrypted, this user who has logged in, if he is able to successfully log in, and probably he can read this file in the unencrypted format. So once this is in an encrypted format or the decrypted format, all the usernames and passwords are still in the plain text format. So once the decryption is done, again all usernames and all passwords are exposed to the user who can read that file. So if you lose the file at this juncture, then again the whole set of username and passwords are compromised. So this also, the second approach, which actually taking the encryption approach, is also not a good way of maintaining the passwords. Now the next question is, what else we can do to protect? If this is not, encryption is not the best way, what I can think of is, the previous case we were using a single key to encrypt the entire file. So can we build little more changes into this one? So instead of encrypting the file with single key, what I can think of is, can we have one different key for every user? Maybe one key for the username 1, and second key for user 2, and third key for user 3, and so forth, nth key for username n. So in that scenario, I still do the encryption, but username and the corresponding password of user 1 is encrypted with the key k1, and similarly the second username might be encrypted with the key k2, and so forth. The nth username and the corresponding password is encrypted with the nth, nth key. And similarly, when I transform this, encrypt this, I might have a differently looking password, and the username might be, now it might have turned into some p1t, and the corresponding password p1 might be, when you encrypt you will get randomly looking text. This is 1 to n, and the second username might be encrypted with the maybe xy1, and then this is 98p, something like that. So all the username and passwords are now encrypted with the different keys and then kept in this file. So how does the verification happen here? Again, a user, once he submit, let's say he claims I am the user, ith user, and he gives a password pi, and now the decryption has to happen. Since I have got n different keys, so what I can do is take this UI and decrypt this username portion, and let's say it maps to username u2. So one time I try with k1, second time I try with k2, and so on. I try with n. So whenever there is a match, I take that username and also the corresponding password, decrypt that, and then if the corresponding password matches, I say this is the success. The user is allowed to log in. So this seems to be again a workable solution. So since the decryption happens one row at a time, and even if you lose this file, as long as the keys are kept secret, then you may not lose anything. So protecting the keys is now important thing. But now the question is, how do we actually manage the keys within the system? And now not only there is one key, but there are n key. As many users are there, those many keys are there. So we started with the encrypting the key because we had the danger that the password file can be read by someone. So we don't want the others users to read the password. But where do I keep the keys? Keys also need to be kept somewhere in the system. So if the passwords can be stolen from this system, if I keep the keys in some other file, those keys can also be stolen. So in nutshell, what I am trying to tell you is, the fundamental problem which you wanted to address is not addressed at all. What we did is, by encrypting the password file with some keys, one key or more than one key, we shifted the goalpost. Instead of protecting the password file, now we shifted the goalpost to protecting the file containing the keys, or some format, in some format. So we need to protect those keys as well. So this is actually going nowhere. So in that sense, encryption, whether with one key or with the different keys for each user, is also turning out to be not a good solution to manage the user accounts and the passwords on the system. Now, if this is not the good solution, what else we can do? How exactly the operating systems actually manage the user accounts and the corresponding passwords? So this turns out to be an interesting question. And most of the operating systems, in fact all the authentications that which use the password, username and passwords, use this as a method. There is something called hashing function. So what they use these hashing functions. The hashing function, let's call that function as f, has got some interesting characteristics. What are these? If I supply some input to this function f, the arbitrary size input, it takes this as an input and it generates some fixed size output. What it means is, if I give 1 byte data, then also it generates the fixed size. Let's say this is the 10 byte output. If I give 1 byte input, then also it generates the 10 byte output. If I give 2 byte input, then also it generates the 10 byte output. If I give 100 byte input, then also it generates the 10 byte output. If I give 1000 bytes, then also it generates the 10 bytes. So you can think of any arbitrary size input you give, it still generates the same fixed size output. And second thing about this function is, hashing function is, if I give any input, maybe let's say my password is name not. So if I give this as an input to this function, computing the output, the fixed size output, maybe the XYZ123 is the output that gets generated. So this computation is easy, transforming the input to and mapping that into some output is an easy operation to do. But what is interesting is, if I give this as an input and if I want to go back to what was the original input, I want to get back this. This is called the inverse operation. If I give this input, finding this one is actually very difficult task. So this is the fundamental characteristics of this function. So such function, which is an essential characteristics of this hashing function, is called as, the function is called not invertible. So one way it is easy, but the reverse or the opposite of this is actually very difficult task to do. So this is one fundamental characteristics. So most of the password management systems uses these characteristics of these functions and then store the passwords. So that is what it is. Let's see how exactly it can be done. So remember, before we actually go into discuss that, this fixed size output is actually in some form is a kind of, it maps many possible inputs into one input. So f is here and I got some input here, maybe I got an a, a small a capital B or a B, and then irrespective of what is the size, I got an A, B, C, I got X, Y, G, A, whatever it is, 1, 2, 3, A. So there are, you can think of possibly infinite values, and irrespective of what is the size, you got only those 10 bytes of the output. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. So maybe 2 is the next entry, and 9999 might be the last entry. 10 digits, 3, 6, 9. Okay. So right. So one input might be generating this a, when I pass it to the function f, it might be mapping to this one. Similarly, when x, y, g, a is given as input, that might also generate the same output, because remember, these are the only possibilities that I got on the range on the right hand side. But infinite input can be anything. There are infinite possibilities. So infinite possibilities are mapped to the only the finite possibilities on the right hand side. So but irrespective of what is the, whatever might be the input under the definition of f, we need to have some corresponding output. So this turns out to be a kind of many-to mapping, meaning many different values in the domain can map into one output on the right hand side. So if I give in our context, what it means is, if my input password is A, then also 1 2 3 4 5 6 this hash value generated. If my password is XYG and A, then also the same hash value is generated. So if I give you this value 1 2 3 4 5 6 7 8 9 0, then figuring out whether A generated this hash value or XYG generated this hash value, we will not be able to get it out, because there might be many other possibilities which actually generate the same hash value. So this is how it actually works. So knowing that what is the hash value does not tell you anything about what is the corresponding password. Although if let's say I and you or the user 1 and user 2 accidentally choose the same password. So maybe user 1's password is XYG and user 2 also chooses XYG as the password. Although when I supply this to function app, they generate the same hash value. But even if I got access to this hash value, whether XYZ generated this or some other possibility XYZ generated, that confusion is still there. Alternatively, what it means is, if my in corresponding hash values 1 2 3 4, this might be the hash value of the password correspond to the user 1, and some other user u2 has also generated some chosen some other password, and if its hash value is also this one, the password itself might be different one, but the verification at the time the hash value does not tell you anything about the password because of this many to one mapping case. So most of the operating systems actually use this as a means to manage the password. Basically, your password is hashed and stored using this one-way async function. I said hashing function generate a fixed size output. Now the question is, how do I what exactly goes inside that function which generates the fixed size output? There are many ways of generating the fixed size output, but let's take a simple example of what you can do. So one of the simple thing that you can do is take the password as an input and get the ASCII values corresponding to all the characters within the password and jar them. So let's maybe take this example. My password is, let's say, Aminath. What I do is I take the first letter N and corresponding to that the ASCII value 10101010. This is a hypothetical number. Let's say this is the ASCII value corresponding to the binary value corresponding to the letter N. Then similarly for second character E, I might have another sequence of binary sequence like here. And what I do is I do a jar operation between this. I'll get some binary digit in here. So this is 0 0 0 1 0 1 1 0, something like this, and then I take the third character M corresponding to that. I might have another sequence, something like this. Again, I do the jar operation and I continue doing this. After as many number of characters are there, whatever the binary number you get to at this place, this becomes the fixed size. So this is the simplest form of the operation, so that you can think of, just to take the all the characters within the password and then jar them and store it in, well, so this is a fixed size output. Although this is not a good hash function, but just to give an idea what exactly goes inside hash function, I just took this is. So similar kind of the operations can be done inside the hash function, which actually transform the input to some form of the output, which is the of the fixed size.